I had a thought the other day. What would happen if you got to OLL and you could predict exactly how every piece would move and know exactly what PLL you had? One step further, could you look at it from simply two sides and do the same thing? Could this lead to two-sided one like last layer? I wasn't really sure, so I decided to find out. You might have heard of two-sided PLL recognition before, but have you ever really known how it worked? Is it just random luck that we're able to distinguish every single PLL by just two sides? Or is there something different involved? Well, obviously, we can see the 6 colors that are shown to us on the two sides. And with corners, you can use the color scheme to know exactly which color is on the backside, given only 2 of them. As you can see here, depending on which color is on the top, the other 2 colors will be swapped, so we can use the color scheme to figure out what the other color is. For example, in this case, I might want to check if the back color of this is yellow or white to solve it with this edge. Now I could use deduction or other strategies, but for corner orientation, we would look at the color scheme. Since if white was on the back, it would be red-blue, but in this case, it's blue-red. So we know the back is yellow. I encourage you to experiment with color schemes yourself so you can figure out how to use this in your own solves, because I think that'd be more valuable and you'd remember it easier. This means that we have access to 2 edges, 1 corner, and these 2 corners as well. When given this, we also have access to the last corner, since there can only be 1 type of every corner, and again we can use the color scheme to figure it out. That only leaves these last 2 edges that we don't see. And since 2 edges can't be swapped, two-sided PLL recognition will always work. So how can we deduce what a PLL is based on 2 sides, instead of just memorizing the order that the colors are in? Well, you have 2 types of swaps: corner swaps and edge swaps. There can only ever be an even number of these, which allows us to figure out what the edges and corners must be on the cube, and thus the PLL. In this example, we see the red-green corner, orange and blue edges, and 2 blues on the bookends. Using corner orientation, we can figure out the colors behind these 2 corners. Because it's a yellow top, this is going to be orange, and this is going to be red. Because of this, we can figure out that this back corner is the orange-green corner, which is going to go green here and orange here because of the color scheme. Now, obviously, I've already showed you what the answer to this one is, but let's figure it out. Here is 1 corner swap, and since we already know these corners are solved, and this edge is solved, it's impossible for these to be anything other than just 1 swap here. If it was to be something like a U-perm, that would be 1 swap with the corners, 2 swaps, and 3 swaps, which we know doesn't work. So this has to be just 1 corner swap here and 1 edge swap here, visualizing into a T-perm. This example is a little bit harder, and it's where I'll start talking about anchoring. Your PLL won't always be lined up exactly on your cube for you, so you have to decide which pieces are solved. It doesn't matter which ones, as long as you keep it consistent, and then you can base your swaps off of that. In this case, we have the orange-blue, blue edge, red edge, and green bookends. With the color scheme, that means on the outside of this green edge, or green corner, is red, and this one is orange. With that knowledge, we know that the one back here has to be the red-blue, which, with the color scheme, blue would be here, red would be here. Now we're going to use anchoring. We know there are headlights along this side, and we're going to call those all solved corners, which means that these 2 are swapped. I'm going to line it up to make it a little bit simpler, but you kind of get how this goes. Alright, so now these 2 are swapped. And then pairing our edges against these headlights over here, we know that it can't be just an H-perm like it looks here, because that would lead to an odd number of swaps. In this case, we can swap red here to go to where it needs to go, as it is a red hole there, and then bring the green over here. Now we don't yet know that this is a green, but we can deduce it based on knowing that we would then have to swap that with either back here or up here, and then swap it again. So assuming we didn't know anything, we'd swap red here, and then get some color here, either orange or green. If it was orange, it would be solved, which we know doesn't work. So it has to be green. Then we would swap green with here to solve it, and we'd swap the blue and orange here to solve this. If you can visualize this, that means there's red headlights over here, and then orange here, as well as an orange here, leading to a block back here, which is a GC perm. So what about for OLL? Surely having all the pieces oriented differently would make a difference. Well, actually, as it turns out, it doesn't really matter how the piece is turned. For corners, you'll still be able to find all the colors. For edges, you'll still be able to deduce which is which. And as piece twisting is separate from piece swapping, it doesn't actually really matter if they're turned or not. We'll still be able to find all the colors and figure out what all the pieces are. So now, to get one look last layer, all we have to do is memorize how every single OLL affects the pieces of the cube, predict exactly where they'll all go, and then figure out which PLL you have. For which you have one look last layer. Yeah, right. Ain't nobody doing that.